So you can see in this video where our goals are to look at a lot of different configurations for amplifiers for op amps. So we're going to look at a lot of different circuit configurations for the op amps and be able to look at the difference. Now, in the previous lesson we talked about railing and saturating op amp. All of those discussions still apply for all of these types of amplifiers, that you can rail the op amp depending on the power supply. Now the circuits we're going to draw are going to be without the power supplies, just to make sure the diagrams aren't so messy, and we'll do the formulas. Now we're going to say here, the first thing is we're going to do the inverting op amp revisited. So this was our inverting op amp. Actually, instead of always drawing that voltage source, what I'm going to do here is just draw them like this, with this being Vin here. So, and when I draw it like that, that means I'm attaching some kind of voltage source here, okay? So I'm just ignoring always drawing that. And then what we did, this was R2, R1, and then we had this just connected directly to ground, and we said here that the formula for this is that V out is equal to negative R2 over R1 times Vn, which is 100% correct. Nothing wrong with our analysis or anything like that. However, let's talk about in practice, because you could wire this up, and in fact, if you wire up in one of your labs here, or just even on your own time, wire up an op amp and have it connected like that, it will work just fine. But good practice is to actually, instead of having it tied directly to ground, is to put a resistor on the positive terminal to ground, and then the resistor value is R1 in parallel with R2. And the reason it would be parallel is, imagine turning both the output voltage and input voltage off. These would be connected to ground, and this would be connected to ground, and so R1 would be in parallel with R2. And you might say, well, why am I putting that additional resistor there? There's no current that's flowing through this. But remember, when we said there was no current, the no current, this is an ideal assumption. The reality is that there are small input currents, and so there are actually small currents, bias currents, that get drawn in on both inputs. But by doing this, what we've done is basically, by adding, here I'll put it here, by adding, just a second, my pen wasn't working quite right, by adding R1 in parallel with R2, the voltage drop at the positive terminal is offset by the same amount as the negative terminal. And this is often called what's referred to as an input offset voltage. And the idea is that when you connect this directly to ground and you put up a voltage here, and you do the computations, there is some offset that happens here. So because of the bias currents that are going into this negative terminal here. So you might put let's just say 5 volts in here, but this is exaggeration, but really then, you're in essence, quote, with the offset voltage, you might have 5.1. But then if you put these resistors here, you would have that this, instead of being connected to ground, would be connected to 0.1 voltage because of the small bias currents, and so that offset voltage here would be the same. Now some op amps will have the ability to even control offset voltages with external pins here, where you can control offsets with additional pins here. Now that's getting into some advanced design, but it's good to get into the practice here. So what is the takeaway from this? Well, here the takeaway is this is my formula. This is my circuit. If I could draw it. This is my circuit here. That's my takeaway. And that this purpose here, this is just good practice. Meaning if I had connected that straight to ground, it's not that it's wrong, it's good practice to do that. Okay? Alright, so let's move on here. We have the non-inverting amplifier. Well, the non-inverting amplifier configuration, well, the circuit looks like this. So this is non-inverting amplifier. And the circuit looks like the following. Oops, I should give myself some space to draw the circuit actually. So we have a V in and a V out, but notice here it looks very similar. I'm going to even scroll back up. It looks very similar to the inverting op amp, where you've got the R1 and R2 attached to the negative terminal there. I still have R1 and R2 attached to the negative terminal, but the difference here is that R1 is attached to ground then, and the input is on the positive terminal here. And so for this, the output equation here, V out is equal to 1 plus R2 over R1 times V in. Now, we could go through all of the analysis techniques that we did in the previous lesson to come up with this formula, but I don't find that there's necessarily any more insight into it. It's the exact same kind of analysis. We just have slightly different things that we have to be concerned about. So this is the formula here, but what we should notice here is, first off, we got this 1 plus R2 over R1. So what that means is a non-inverting amplifier always has to have a gain of at least 1. There's no way, so this gain is always at least 1. Greater than or equal to 1. There's no way to make the gain less than 1 because I've got that 1 plus R2 over R1 business going on. And then also notice that, of course, it's non-inverting. Whereas in the previous formula, we had a negative sign coming there. Clearly everything's positive here, and resistor values are always positive. So my output is positive, and so it's still amplifying because I'm still getting a gain, and we can see clearly it's not inverting. So hence the non-inverting amplifier. Another amplifier that we can look at is the summing amplifier. Now this is really a bunch of inverting amplifiers. So I'm going to draw here, make sure I get myself enough space. And I'm going to draw it two ways here. I'm going to first just tie the thing directly to ground here. And then what I'm going to do here is come up and we're going to put, let me redraw those a little bit nicer. So we've got 3 different voltages coming in. And then V out coming out of there. So this is a summing amplifier, and you might say, well, why am I summing up just DC voltages? You know, DC voltages you might not necessarily sum up, but you want to think of these voltages. They're not necessarily DC voltages. These could be sounds, like frequencies. So these could be 3 different signals at 3 different frequencies that you want to sum together, either for transmission, or maybe you're just summing them together because you're going to drive like a speaker, for instance. You know, maybe this is, you know, treble, bass, and, you know, mid, and you're wanting to, you know, be able to adjust the amplification on the treble, bass, and mid, and then you're going to sum those signals back up because you don't want them separate and send them to your speaker. You know, so I mean, that's possible. Something else that you could be using with this summing amplifier. But the formula here for this, the V out here, is equal to a negative, and I'm going to put this in square brackets here, R4 over R1 V1 plus R4 over R2 V2 plus R4 over R3 V3. Now, an easy way to derive this formula is using something called superposition, which is probably in your textbook. We didn't discuss it, but that's an easy way to derive this formula for us. But really what we can see here, if we just examine this, this is really just, you know, hey, that's an inverting amplifier formula, that's another inverting amplifier formula, and that's another one. And why are they all? Because I've got this negative out in front that would factor into each one of those. So really, we are literally summing up the signals, but yes, we are gaining some gain. Now, if we want no gain, if we want to literally just sum with no gain, you guys should be able to figure this out. Just think about it in your head. How would I sum with no gain? Well, you just set R1 equal to R2 equal to R3 equal to R4. So all of these ratios here would become 1, and so you would get V out is equal to negative V1 plus V2 plus V3. Now, again, we can make it so we get gain. Now, let's go back to the circuit diagram. If we think about this, because this was just inverting amplifiers, we could think about, well, wait, we could just connect that positive terminal straight to ground. But again, if we go back to what we did with this inverting amplifier, good practice is not to just attach the positive terminal straight to ground, but it's to put a resistor there in for an offset voltage for real op amps. And I'm going to put a resistor in here. And again, this is for good practice. When I say good practice, this is good engineering practice, which doesn't always occur, but this is good practice here. Whoops, draw. And you can probably guess what it's going to be here. It's going to be R1 in parallel with R2, in parallel with R3, in parallel with R4 is what you'd want that resistor value to be. Now again, if you tied it directly to ground, it will still work. It will still do its summing. Nothing, you know, too fancy about that. But good practice would be to do it this way. All right, so we've got 2 more amplifiers to discuss. We will do some examples with some of these amplifiers as well, but I'd like to discuss them all and then do an example where you then have to look at the circuit and identify what kind of amplifier it is in order to know which formula we need to apply. So the next amplifier that we're going to look at is the difference amplifier. and we'll say that this is V1 and this is V2, and then we actually have some resistors that we're matching here. So R1 and R1 just means they're the same resistor value. R2 and R2 means again that they're the same resistor value here. And we do that on purpose. You can derive a formula with, you could have 4 different resistor values and derive a formula with that. It's not that you can't do that. You can do that. It becomes a little bit more cumbersome. It doesn't turn out to be as nice of a formula. And if we're really wanting to do a difference amplifier, we're really wanting to just amplify the difference of these two voltages. So if we want to just do the difference of those two voltages, what we look at here is we would say then that V out, here the formula for this is going to be R2 over R1, which is our gain. And now it's actually not what you might think it would be. Your guess, actually I'm sorry, it is exactly what you think it would be. It would be V2 minus V1, the voltage on the positive terminal minus the voltage on the negative terminal. Now again, if these resistors aren't matched, you're going to have something like, an R4 over R3 times V2, minus an R1 over R2 over R1, V1. You're going to have a much more complicated formula. And so that's why we tend to match them, because again, what's the goal here is that we want to amplify the difference. And we can see there's not any kind of external offsets or anything that we need to add with regards to that circuit here. Now, this here, I'll put a note here. Need to use what I'd call precision resistors, and where the tolerance, I would say R tall, is less than or equal to 1%. Now I believe most of the resistors you have in your kits are 5% resistors, and if you have 5% resistors, we can get some other things going on, and maybe I'll put that in another video here. You can also research that as well as far as it, but even with the 5% resistors, we can still do an experiment with it. It just won't be precisely what we think it should be. Alright, now we've got one more amplifier, and it's not even really an amplifier. It looks like something that, why would you do this here? So this is called a voltage follower, and we'll talk about this on why you would want to do this. This is a voltage follower. That stands RL for the load resistor. And so I put an input on the positive terminal, and then I tie the negative terminal to the output there. This basically gets me V out equals Vn. So why ever use it? This is because, why would we ever use it? Well, there's several reasons. The input resistance is high. Remember, it's in the mega ohm range, even higher than mega ohm range sometimes. And what that can enable us is that basically it can account for loading effects in a previous stage of a circuit, and also if the input were to be disconnected, such as when coming from an external sensor, we can tie the input to ground via a high value resistor. So that keeps the input at ground as well. But let me show you an application of why you might want to do this. There's lots of applications for this, but this is something that we haven't necessarily talked about here, but this is going to be a filter here. And I know these are capacitors. We haven't talked about them too much. Plus minus Vn. And let's just say this is 1 kilo ohm and 1 microfarad. I don't even know if those are correct values for what I want to illustrate here, but it will serve the purpose. So let's assume then we want to connect, this is filtering a signal, and we want to connect this up to like a speaker. Well, we know that speakers have low resistance, like 8 ohms. If I connect this speaker directly up here, like this, we're going to have a problem. The 8 ohm is going to load the 1k ohm, and we will have a circuit that looks like this. And because the reason it's loading is you can see that this 1k is going to be in parallel with that 8 ohm resistor. So if you do 1k in parallel with 8 ohms, you're going to essentially get 8 ohms, and this will still be 1 microfarad. But what we've done here is this is critical. The filter properties have changed. This filter does not have the same properties as this filter up here because it's now getting this loading effect from that 8 ohm resistor. Well, one way to take care of it, it's not the only way, but one way you can take care of that is you can simply do, okay, well, I've got my 1 microfarad, my 1 kilo ohm, and then we're going to connect this up to a voltage follower, which is then going to be connected to my 8 ohm speaker. And now this has a really high input impedance. If you do 1 meg in parallel with 1k, you still get 1k. So this filter spec hasn't changed at all over here, and I'm able to still get a low output impedance, because op amps have a low output impedance of like 75 ohms or something, which it's like that doesn't match. If this is my load, well, what you can do here, and what sometimes you can do, is I can say, okay, well, I can drop another in my circuit here, 10 ohm resistor, to drop the output impedance of the op amp down such that I match this 8 ohm. And then typically you have some other capacitors for filters and stuff like that. But the point is that now this filter here, this very simple filter, hasn't had its specs changed, the cutoff frequencies changed due to this loading effect. So that's one application of a voltage follower. There's lots of applications for it, but sometimes when people say, it's like, well, why would I ever want V out to be equal to V in? And the reason is well, you often want something that has a high input impedance and a low output impedance, and we can do that with a voltage follower. So if I don't want gain, I can just throw this in here, as sometimes they're even just called buffers, as a buffer. So those are some basic circuits. These are by no means a complete list of op amp circuits, but we're going to look at some examples here in the next video.